Welcome back, and we're going to focus on Chapter 6 here. And within Chapter 6, focus on business intelligence and specifically databases and information management. So this slide describes a hierarchy of data that is used to store information in a database, progressing from the database as the top level holder of information down through the field, which stores information about an entity's attribute. This hierarchy is illustrated by the graphic on the next slide that we will take a look at. A computer system organizes data in a hierarchy that starts with the bit, which represents either a 0 or a 1. Bits can be grouped to form a byte to represent one character, number, or symbol. Bytes can be grouped to form a field, and related fields can be grouped to form a record. And then related records can be collected to form a file. And related files can be organized into a database. So this graphic illustrates the hierarchy of data found in a database. It shows the student course file grouped with files on students' personal information and financial information that form the student database. Excuse me. It illustrates what data is found at each hierarchical level from the database level down, making up the smallest information unit, the field, or smaller units of data common to all applications, bits and bytes. A bit stores a single binary digit, 0 or 1, and a byte stores a group of digits to represent a single character, number, or other symbol. This slide discusses the problems in data management that occur in a traditional file environment. In that environment, different functions in the business or functional units, such as accounting, finance, HR, etc., maintain their own separate files and databases. This graphic illustrates a traditional environment in which different business functions maintain separate data and applications to store and access that data. What kinds of data might be shared between accounting and finance and HR? What about between sales and marketing and manufacturing? The use of a traditional approach to file processing encourages each functional unit in a corporation to develop specialized applications. Each application requires a unique data file that is likely to be a subset of the master file. The subsets of the master file lead to data redundancy and inconsistency, processing inflexibility, and wasted storage resources. This slide defines and describes databases as compared to database management systems, or DBMS. What do you think the difference is between a database and a DBMS? What is the physical view of data? What is the logical view of data? A single human resources database provides many different views of data depending on the information requirements of the user. Illustrated here are two possible views: one of interest to a benefits specialist and one of interest to a member of the company's payroll department. This graphic illustrates what is meant by providing different logical views of data. The orange rectangles represent two different views in an HR database, one for reviewing employee benefits and the other for accessing payroll records. You can think of the cylinder as the physical view, which shows how the data are actually organized and stored, on physical media. The physical data do not change, but a DBMS can create many different logical views to suit different needs of users. This slide introduces the most common type of DBMS in use with PCs, servers, and mainframes today, the relational database. Why are these DBMS called relational? Can you think of any examples of relational database management systems popular today? And if you've used any of those? A relational database organizes data in the form of two-dimensional tables. Illustrated here are tables for the entities supplier and part, showing how they represent each entity and its attributes. Supplier number is a primary key for the supplier table, and then a foreign key for the part table. The graphic on this slide illustrates two tables in a relational database management system. The key field in the supplier table is the supplier number. This slide describes how information is retrieved from a relational database. These operations, select, join, project, are like programming statements and are used by DBMS developers. For example, looking at the last two slides showing the supplier and parts table, you would use what kind of an operation to show the parts records along with the appropriate supplier's name. Microsoft Access, for example, has wizards for these commands. The select, join, and project operations enable data from two different tables to be combined and only selected attributes to be displayed. So this graphic illustrates the result from combining the select, join, and project operations to create a subset of data. The select operation retrieves just those parts in the part table whose part number is 137 or 150. The join operation uses the foreign key of the supplier number provided by the part table to locate supplier data from the supplier table for just those records selected in the select operation. Finally, the project operation limits the columns to be shown to be simply the part number, part name, supplier number, and supplier name within the orange rectangle. This slide discusses the three main capabilities of a DBMS: data definition, the data dictionary, and a data manipulation language. For a large company, a data dictionary might also store characteristics such as usage, ownership, authorization, security, and users. Note that the data manipulation language is the tool that requests operations such as select and join to be performed on data. Again, an example, Microsoft Access has a rudimentary data dictionary capability that displays information about the size, format, and other characteristics of each field in a database. Displayed here is the information maintained in the supplier table. The small key icon to the left of supplier number indicates that it is a key field. This graphic shows the data dictionary capability of Microsoft Access. For the field supplier name, Selected in the top pane, definitions can be configured in the General tab in the bottom pane. These general characteristics are field size, format, input mask, caption, default value, validation role, validation text, required, allows zero length, indexed, Unicode compression, IME mode, IME sentence mode, and smart tags. Illustrated here are the SQL statements for a query to select suppliers for parts 137 or 150. They produce a list with the same results as the earlier figure we discussed. This graphic shows an example SQL statement that would be used to retrieve data from the database. This graphic illustrates a Microsoft Access query that performs the same operation as the SQL query in the last slide. The query pane at the bottom shows the fields that are requested, so fields, the relevant tables, the fields that will be displayed in the results, and the criteria limiting the results to part numbers 137 and 150. This slide describes activities involved in designing a database. To create an efficient database, you must know what the relationships are among the various data elements, the types of data that will be stored, and how the organization will need to manage the data. Note that the conceptual database design is concerned with how the data elements will be grouped. What data in what tables will make the most efficient organizations. An unnormalized relation contains repeating groups. For example, there can be many parts and suppliers for each order. There is only a one-to-one correspondence between order number and order date. The graphics on this slide and the next illustrate the process of normalization. Here, one table lists the relevant data elements for the entity order. These include all of the details about the order, the part, and supplier. An order can include more than one part, and it may be that several parts are supplied by the same supplier. However, using this table, the supplier's name and other information might need to be stored several times on the order list. After normalization, the original relation order has been broken down into 4 smaller relations. The relation order is left with only 2 attributes, and the relation line item has a combined or concatenated key consisting of order number and part number. This graphic shows the normalized tables. The order table has been broken down into 4 smaller related tables. Notice that the order table contains only 2 unique attributes, order number and order date. The multiple items ordered are stored using the line item table. The normalization means that very little data has to be duplicated when creating orders. Most of the information can be retrieved by using keys to the parts and supplier tables. It is important to note that relational database systems try to enforce referential integrity rules to ensure that relationships between coupled tables remain consistent. When one table has a foreign key that points to another table, you may not add a record to the table with the foreign key unless there is a corresponding record in the linked table. For example, foreign key supplier number links the part table to the supplier table. Referential integrity means that a new part can't be added to the part table without a valid supplier number existing in the supplier table. It also means that if a supplier is deleted, any corresponding parts must be deleted as well. This diagram shows the relationships between the entity's supplier, part, line item, and order that might be used to model the database in Figure 610. One technique database designers use in modeling the structure of the data is to use an entity relationship diagram. Symbols on the diagram illustrate the types of relationships between entities. This graphic shows an example of an entity relationship diagram. It shows that one order can contain many line items. A part can be ordered many times and appear many times as a line item in a single order. Each line item can contain only one part. Each part can have only one supplier, but many parts can be provided by that same supplier. This slide discusses other types of DBMS. Why would one want to store social media data in a non-relational database? The answer is that social media involves many different file types, and the information is not easily organized into tables of columns or rows. Another option for businesses is to license database software from the cloud. This slide continues the discussion of other types of DBMS. Another option for businesses is to license database software from the cloud, as I mentioned earlier. What would be an advantage to using a database service such as this? Primary answer is scalability. You pay only for the exact services that you need at that point in time. Blockchain is a transaction database that uses encryption to ensure the validity of transactions among the parties in the system. Blockchain will be discussed more fully in Chapter 8. As we look quickly at blockchain, a blockchain system is a distributed database that records transactions in a peer-to-peer network of computers. This slide discusses how very large databases are used to produce valuable information for firms. The text gives the example of Shutterstock, a global online image marketplace with over 24 million images, which, by analyzing big data, is able to find out where its website visitors place their cursors, how long they hover over an image before making a purchase. Business intelligence is a very amorphous notion that is not well defined. In this course, we'll refer to instead to business intelligence environment, which is composed of many different components, including both technology and the management dimensions. This slide discusses the use of data warehouses and data marts by firms. Why is having a data warehouse an advantage for firms hoping to perform business analysis on the data? Why does there have to be a repository of data that is separate from the transaction database? Hadoop is one of the tools used by search engines such as Google and Bing to rapidly search billions of web pages and find those which appear to be the most relevant to a user's search query. That task is accomplished in a few milliseconds by distributing the data and the processing across tens of thousands of processors and then pulling the results together to produce a web search page for users. Hadoop is far faster than SQL and traditional centralized databases running on very large mainframes or supercomputers. It's also an open source software library. This graphic illustrates the components of a contemporary business intelligence infrastructure. It shows that the data warehouse extracts data from multiple sources, and both internal and external, including a Hadoop data lake, and transforms it as needed for the business intelligence systems. An analytic platform has tools for power users, including reporting, OLAP, or online analytic processing, and data mining to extract meaningful information from the data warehouse and Hadoop data lake. A subset of the data warehouse is collected in a data mart for casual groups of users. This slide describes the role and types of analytical tools and techniques for finding useful information and relationships in large data sets. Here we discuss online analytical processing, one of the three principal tools for gathering business intelligence. This graphic illustrates the concept of dimensions as it relates to data. Product is one dimension. East is a dimension, and projected and actual sales are two more dimensions. Altogether, we are trying to analyze four dimensions. The business question is, in the Eastern region, what are the actual and projected sales of our products, or nuts, bolts, washers, and screws? Sometimes referred to as a data cube, the graphic can depict this four-dimensional view of the data. More importantly, when compared to a spreadsheet model of the same data, a graphical data cube is much faster and easier to understand and visualize the relationships. This slide discusses another business intelligence tool driven by databases, data mining. Data mining provides insights into data that cannot be discovered through OLAP by inferring roles from patterns in the data. Whereas data mining describes analysis of data in databases, there are other types of information that can be mined, such as text mining and web mining. Ask students what other types of unstructured textual data sets a company might store and what kind of useful information might be extracted from them. This slide continues the exploration of mining stored data for valuable information. In addition to text mining, there are several ways to mine information on the web. The text uses the example of marketers using the Google Trends service, which track the popularity of various words and phrases used in Google search queries to learn what people are interested in and what they are interested in buying. What type of web mining is this? Why might a marketer be interested in the number of web pages that link to a site? This slide looks at how companies utilize the web to access company databases. Here, users access an organization's internal database through the web using their desktop PC browsers or mobile apps. This slide discusses the firm's need for data governance in order to ensure that firm data is accurate, reliable, and readily available to those who need it. Here, the importance of data quality. Think about personal examples of what happens when a company's data is faulty. The text provides an example of one study finding that 10 to 25% of customer and prospect records contain critical data errors.